Hi, in this video I'm going to show how to use deep learning to classify objects in point clouds. A point cloud is a cloud of three-dimensional points that are taken from a sensor like LiDAR or Kinect. In this example, I'm going to use a point cloud dataset that has a label for a corresponding object that is represented by a point cloud. For example, in this case, we have a four-wheel drive car, a four-wheel drive vehicle, and the corresponding point cloud points. As you can see, the silhouette, the shape of the car. And notice that since this is coming from a radar-like sensor, you're going to see only the points facing the observer. The points behind the car that are not visible to the observer are not going to appear in the point cloud. Okay, so these sparse set of points are going to be pre-processed and converted into a contiguous three-dimensional array that can be fed to a convolutional neural network that is going to perform the classification. Most of the example is going to go in the effort of pre-processing the data. We're going to use some data augmentation to overcome the bias in the data. So let's take a look at the example. MATLAB offers two variants of this example. One of them is using custom neural network training, and in this case a layer network is not used, but rather that the network is implemented by manual functions. For example, here the gradients you call the point classifier, that is basically you're gonna do the weights manually and do all the computations, and using DLRA and DLF-eval you basically compute the gradient and manually you call the adaptive momentum update to update the weights using the gradient. So basically this is the manual training. This example is very long. I'm going to put this in the reference in the description, which is below this video, but I'm going to do the easier version that actually has a better accuracy, in which a layer network is created like this. Just specify the input layers, convolution, ReLU, max pooling, etc. We create the VoxNet neural network. We provide the training options. We provide the data store for the training and use the train network function that is going to create the trained deep learning model. And with that, we perform classification, and then we evaluate against the validation set to verify the accuracy. And you can see that the author was able to get 72% accuracy. And finally, we use a confusion chart to check for the accuracy. Okay, so to try the example, let's here open LiveScript, and that'll take us to the MATLAB desktop. So I made a slight modification to example. I have a local SSD drive, so if I use this method to download the dataset, it's gonna download it into my C drive, and I don't want that, so I want to use my magnetic drive, so I specify it here. Okay, so let's run this and download the dataset. And yeah, these functions are part of the example. If you click at the link that I have below, you're gonna see the full example, and all these functions appear at the end. And so it's just gonna do untar and download. I already downloaded, so it's not gonna do it again. And then I'm gonna load. So I'm gonna have, if you take a look at the data, you're gonna see that there are 4 folds. Each of these has a bunch of files with PC clouds, and I'm gonna use the first 3 for training and the 4th one for validation. When you train a neural network, you want to use a set for training, a set for validation, and a set for testing. Testing is when you already have your trained neural network, you want to check the accuracy against that independent testing set. You're not supposed to use the validation set for testing, but this example is doing it, I guess, for simplicity. But by having the test set being equal to the validation set, there's some bias that is being introduced into the model. It's undesirable, but it's just an example. Okay, so let's load the data. Let's go inside this function, And so we're gonna load this text file, which is gonna give us the list of point cloud file names. So for example, the first fold is gonna have all these files, and we have the relative folder, which we are gonna append to them. So yeah, so we have selected only the first 3 of them and concatenated, and now we have 433 files. This is just the name of the file. And notice that the name of the label appears in the name of the file and should match the label that we're going to use. In this case, these first 5 files are for 4-wheel drive vehicle, for a building, etc. We're going to append the relative path. Now we have the full path for them, and we're going to pass all those files to create a file data store, and the file data store is going to read for each of those files. It's going to apply a callback function, and this callback function is going to return us the point cloud and the label. In one column we're going to have the point clouds, and the other column we're going to have the labels. Okay, and the format is bin. It's a bin file. Okay, so now also as you could see, the files are in order, so that could introduce some skewness into the training, so we want to shuffle them. So we're going to create a random permutation of the indexes, and then apply that permutation into the files, and then reassign them to have them in a shuffle order. So now you see that we don't have the same label. It happens here a couple of times, but it's just 2. Okay, so we already load the training data, and we're going to do the same for the validation data. I'm not going to go inside there. So now for the training data, we're going to apply a temporary callback. This is a temporary transform object that is going to just take the second column. And so this is for the labels. The first column is the point cloud, so we're just going to take the labels in this transform, and the transform is executed when you read the data. So we invoke the read all, and that's going to give us all the labels. And we're going to see, for example, pedestrian. We're going to see multiple times, etc. And now we're going to plot all the labels just to get that distribution. And the point that the author is trying to make is that this data is skewed toward pedestrians, so pedestrians are going to be detected better than other objects, which is good because we don't want the car to hit a pedestrian. But things like truck and UTE are going to suffer because of the lack of representation. So what we're going to do is use data augmentation to make this data unbiased. So for example, this one is going to repeat it once and over, but using augmentation, and that means yes, we're going to have the same data here, but we're going to apply an affine transformation to it. We're going to move the points a little bit, and also probably we can also put some noise. Okay, data augmentation is a technique that is used in deep learning in general. It is convenient when you have a small set that you want to create more data that is different. Also, you want, especially in computer vision, you want your neural network to be resistant for affine transformation. So it's very common in these augmentation techniques to use affine transformations, random affine transformation on the data. And also you want it to be resistant towards noise, so you can introduce noise in the data augmentation. Okay, so we have this method for data augmentation, which is at the bottom of the example. I'm going to put a breakpoint here. Also, I'm going to put a breakpoint here because I'm going to show later what this is for. And again, when we create the transform data store, the callback is not executed. It's only executed when it is read. We can use a method like read all, preview, or read to get the data. And now we get the data here. We have yeah, actually I should put a breakpoint in here to show how this is done. Yeah, I didn't show how these two are done, but I'm going to show in a moment for the next read. Okay, so we already got the point cloud in here from the file, and we have the label. In this case, it's a boss. So we're gonna get the point cloud, and we're gonna apply an affine transformation to it. This case, the rotation. This is gonna be a scalar. It's gonna be between 0 and 360. So we're gonna apply a rotation between 0 and 360 degrees, and it's gonna be on the z axis. X, Y are 0. So this is the third dimension. Is gonna be the rotation, and DL is just a method to basically pair these two values into the corresponding fields, into the corresponding parameters of the function. That's it. The scale is gonna have a range, so we're gonna make it bigger or smaller by 2% only. We're gonna apply reflection, so we invert the order of the columns in X column, in the X axis, and also in the Y axis. Okay, so this is gonna give us, all these configurations are gonna give us a random affine transformation, and which is represented by this matrix. So all the reflection, all the scaling, all the rotation is going to be, for example, this is a rotation and could also include reflection. We don't see any translation, so this is going to be 0, and in this case seems it might not be scaling. Yeah, I think the scaling is over here, but anyway, everything is captured in this transform. And then there's a PC transform function that takes a point cloud to apply the transform, and now we update the point cloud with that transformation. And now we're gonna apply some jitter, and I'm not gonna go the detail of this, but what this is gonna do is gonna create an array, a three-dimensional array of the same size as the point cloud. The location are just the points. You can see it here, 500, 200, 2000 points, three-dimensional points. So it's gonna be the same size, the same type, which is double, and it's gonna be zeros. And then it's going to populate it with the limits. The limits are the maximum and the minimum in each axis. So it takes the difference and then multiply it by a random number between 0 and 1. But that still is too large. So at the end, everything is multiplied by this small factor. So we're going to get, at the end, we're going to get a set of translations, the very small translations. You can see in here how small they are, and then apply PC transform, which is gonna see this as just a translation in the point clouds. So basically, it's gonna random move the points a little bit, just to be resistant. It's like creating noise. Okay, so now we have the point cloud that is transformed, and the label remains the same, which is a boss. So I think there's a method called PC show that we can see. Yeah, we can use that method, and you can see here that it looks like a boss. Yeah, it's a boss. And notice that we can only see the observer is coming from this side, so we're gonna see all the points in this side of the boss, but we're not gonna see the points in the other side because lidar and all these things are radar like, so the only the observer side are gonna be seen. Okay, so it is a boss. This doesn't change. So now we have our data augmentation. Okay, so let's just continue. Let's just go to here and put a breakpoint here. Hit F5 to go to the next line. Okay. Okay, so now let's another thing is that we have to convert the sparse points, the sparse three-dimensional points of the point cloud into a contiguous three-dimensional array that the deep learning network can read. I already mentioned that most of the work in this example comes in pre-processing of the data, make the data fit the neural network. That's why we're spending so much time into this. So the final part is basically converting this three-dimensional grid sparse points into a contiguous array, and that is done through this callback that we're going to hit with this transform data store that is taken as input the training data and the validation data. Notice that the data augmentation is only done on the training data. We don't have to do it for the validation data. But the conversion from the sparse point to the contiguous points has to be done for both the training and the validation, and the reason is that even after the neural network is trained, you cannot just feed the network a point cloud. It's not going to understand it. You have to do the conversion so that you can classify with the network, and that's why we need this data store to evaluate at the end after training. Okay, again, these methods are only going to be hit when you use the preview method. So let's hit the preview method. Okay, actually I'm gonna hit F5 to jump into here, and that's gonna hit the extract training data. Okay, so we didn't hit this before, but when we read the data from the data store for the first time, it had to go through here. So the first step in the data store, the data stores can be chained like in that decorator pattern. You can put one on top of the other. So we have a chain of data stores. The first link in the chain is gonna read the data from the file, at least in the training data. The second link in the chain is gonna apply data augmentation, and the final link in the chain is gonna convert the sparse points into contiguous points. So we are in the first link of the chain that we have not seen yet. So we're gonna take the file name and we're gonna load the data. Okay, so that's gonna take us to the read bin, which is part of the methods of the example. And I'm not gonna go into the details of this. It was basically reading the X, Y, and Z coordinates and the intensity, which is basically the grayscale color. It's gonna read them from somewhere in the file. So there's a particular format to read the point clouds. Okay, so now we have the three-dimensional points and the corresponding intensity. We have 2000 points for the boss. Okay. So as I mentioned before, the file name has the label in it. This is the first part. So we're gonna take the name and we're gonna just do some string processing and get the name out of it. And which should be one of these labels. And then the label, this is gonna be used to be converted into a categorical. Okay. Yeah, I think it was in the custom training example that this label was turned into one-hot encoding. I'm not sure if this is done here. Probably it keeps the categorical label as an input. Okay, so let's hit F5 because we already have our one more detail. Now, once you have the point data, the three-dimensional points and the intensity, you're gonna create the point cloud, which is an object. I'm just gonna put it in here. And this object is going to have the 2000 points, three-dimensional points. It has the X minimum and maximum, and this was what we used for the data augmentation to determine to do the jitter, and the intensity, which is the color. So for that point cloud, we have a label of boss. That's it, the category. So this is the tuple that is returned by the data store. So let's hit F5. Okay, now we're in the final chain of the data store, which is the conversion from the 3D sparse points into a contiguous array. So there's this function called PCBeam, which takes the data. We're taking the point cloud, which is the first element of the two. We have two elements in here, which is the point cloud and the label. So we're taking the point cloud in here, and we're going to convert it into a grid. Okay, let's take a look at how the grid is a cell array. And let's take a look at it. So it's a 32 by 32 by 32. We have a total of 2000 points, and notice that in this three-dimensional grid, most of the points are zero. It's expected we have sparse points, but some of them have points. Where there are points, we have the intensity. Okay, so if you multiply 32 by 32 by 32, we have 32,000 points, representable points, and from all of those points, we are only using 2000 for this boss. Okay, so we're going to create an array which is going to be zeros initially, and it's going to be of the same type. it's gonna be a boolean, because in the point cloud we have intensity, but here we're just gonna say, okay, you have point or you don't have a point. If you don't have a point, then it's gonna be 1. So let's go over here and take a look at the occupancy grid, and you can see it is a single, but if you use unique, you're gonna see that all the values can be 0, 1, and 32 by 32. So it's basically an array, and you can see that you can see some points, some ones very sparse, but you can see in here this is your point cloud. So now we have it in a contiguous array, and the label is the same. And now the tuple that we return is that contiguous array and the label, and we can see the for watching images, we can use ImShow and the image, but in this case it's board show. And let's take a look at how it looks, the boss. So we have a good representation of the boss. I understand that, well, it doesn't look as well, but somewhat, at least the shape is preserved. Okay, so let's get out of here and just run all the way to this point by hitting F5. And let's take he's basically using an alternative to board show, a little bit more fancy. Yeah, it's basically the same shape that I just showed now. It's a little bit slower to rotate this. Okay, let's proceed. Now we have the data store ready for training. So we need 3 things for training the network. We need the data store, we have it, and also we have the validation store. We need the training options we're gonna get later, and we need of course the network. And for that we're gonna create a layer network in a very simple way. We have the input layer, convolution, ReLU, max pooling, all of this to take all the features. And finally we do the classification with the fully connected layer, max, and classification. Okay, so let's go here and create the layer graph. And this is gonna visualize, but there's a better way to visualize this network by using the analyze network command, and that'll give us more details about the network. And we can see here that it's very simple. We have the input 32 by 32 by 32 as expected. That's the format that is gonna be the network's gonna understand. That's why we need to do the pre-processing, that all the work that we did. It's gonna be a boolean. We don't have colors, so the channel is going to be 1, size of 1. And then after applying convolution, we start to have features, 32 features in particular. And we have a stride of 2, so half of the space is lost. In addition, we don't have padding, so there's an issue. If we have a padding that corresponds to a stride, we will have a 16, 16, 16, but also the corners are lost. Then we have a ReLU for regularization. We have a convolution with no padding, so we lose additional borders, and more ReLU, max pooling to detect global features. And with a stride of 2, we lose half of the half of the size of the spatial dimensions. Then fully connected is to get the classification information, so we change the features for 3228. The spatial dimensions are gone. And then we do some dropout for regularization, another fully connected layer that turns the 128 features into the classification dimensions. I mean, we have 14 categories, so that's why we have to do the switch. And finally, we decorate this with submax and cross entropy to have the final classification. Okay, so now finally, let's get the training options. For the training, we're going to use a mini batch size of 32. We have a total of 433 files for training, and dividing the number of files by the mini batch, we determine the number of iterations per epoch, and we use that to determine the dropout period. So the dropout period is going to be the point when the learning rate is going to be dropped. We start with a high learning rate because at the beginning we have a high error, so we want to have a high learning rate, but as we approach our goal, we want to reduce the learning rate. So we pass the mini batch size, the drop period, the max epochs. We're going to have 60 epochs, and the validation data is passed as a parameter, as an argument for the training options. We're not going to do shuffling, so we have a training options, and now we just execute the train network command, which takes as an input the data store for training, the neural network, and the options that we just created. And the output is going to be the trained neural network. So if you want to deploy this to an embedded system, you just have to save this boxnet into a mat file, preloaded into a persistent memory, and then just invoke the classifying method, and that you can generate code for. It doesn't make sense to generate code for training because that takes a lot of time, and you're not going to do that in a mobile device or embedded system. It is better to do in a GPU or in the cloud. But once the network is trained, you can deploy it by generating C++ code, and I think I have a video for that, or you can search in the MATLAB documentation on how to do it. It's pretty trivial. And yeah, so at the beginning you can see that the accuracy is very poor, but it quickly improves, and it's gonna get all the way to 60. So I'm gonna pause until it gets there. Okay, it finished training and it reached a validation accuracy of 71%, which is pretty good. So let's try it out. Okay, so we're gonna take all the labels from the validation set, and we do that by creating a data store transform that is gonna apply this callback to get the second column, which is the labels, and we just read everything. So this is the expected outcome, and then we apply the classifying method of the trained neural network that we obtained here, and we pass the validation data store. And as I mentioned before, you have to convert the point cloud into contiguous array to be able to feed it into a neural network, and that is what the validation data store is doing, in addition to read the data from the files. Okay, so let's just run it, and that'll give us the actual outputs, the prediction, the classification for all the files in that data store. But that I do not found that very clear. It looks better like this. So classify is really a method that it takes as an input the validation data store, and the output is going to be the classification labels. So this is basically the same. Okay, so now we just compare all the 155 elements returned by the classification method against the expected labels, and the number of elements are 155, so we divide that. So the number of ones, if we have one for all the 155, we divide by 155 and we get 100% accuracy. But if we get some zeros in this comparison, the accuracy goes down. Okay, so just take a look at what happens here. So you can see that there's some zeros, but there are more ones than zeros, which is good. So the accuracy is 71% as shown in here, and the confusion chart is gonna compare the labels, the expected labels, against the outputs, the classification versus the expected, and we can see that the data is biased, so we're gonna have more pedestrians, which is good. It's good not to hit them. So yeah, so basically this example showed how to use deep learning for classifying objects in point clouds. The point clouds, which is sparse data that the network, a convolutional network, can tolerate, had to be converted into a contiguous array. More precisely, a contiguous 32 by 32 by 32 three-dimensional grid, and which is a simplification to be able to train this network fast. For this particular example, it took me about 5 minutes to train this network, and usually to train a neural network it could take hours or days. So as you can expect, if you provide more data, the accuracy would go maybe to 90%. Also, the neural network was quite simple. If you use a better network, the precision can go up. Also, maybe you can use more regularization methods. There are many other strategies that you can use. The purpose of this was basically to show how deep learning can be used for this type of problems that are somewhat similar to what you see in computer vision for images. Okay, that's all for the video. Thank you very much for watching.